Unit number 12, the halogens. This is all about group 7 or 17 of the periodic table in which we call the elements as halogens. To be honest, the word halo means salt and the word gen means forming. So these elements are the one that sort most of the that form most of the salts around the world. That's why we call them salt forming. Moving on, since we're talking about a certain group, and if we go from top to bottom in a group, the elements are fluorine, fluorine, bromine, iodine, and acetylene. Acetylene is the only one which is radioactive, and which, if I say, I'll be safe to say, is still a mystery to human beings. Human beings are still trying to find out about acetylene more and more. We know a lot about these four as compared to acetylene. So whenever we go with IGCSE or A-level book, we tend to simply talk about these four halogens at the time. So these are group 7. They have 7 electrons in their valence shell. They all react the same way. The word means salt producing, and they react with metals to produce a wide range of salts. This includes the salts that we eat every day or the salts that we commonly use in our life. All the salts contain the X negative ion. X negative means they can gain one electron. However, since they are non-metals, they exist as diatomic molecules. They exist as F2, Cl2, Br2, I2. A table at the bottom of the page is going to clear out the idea for us. If we look at the physical states, two of them are gases at room temperature. One of them is the liquid. This is probably the only liquid at room temperature in terms of non-metal in the periodic table. And the last one at the bottom is solid, that is iodine. Now, the color for them is pale yellow and pale green for fluorine and fluorine. There is red brown liquid for bromine, and it is also considered as orange brown vapor because it can vaporize very easily. We call it, I simply miss the word, volatile. We call them volatile because they can easily evaporate. Now, moving on, the next one is iodine, which is a gray-black solid. It has purple vapors, and it is shown over here in the diagram. Remembering their states at room temperature with their formulae and their color is a part of memorization, so make sure you memorize the entire table 12.1. That's also written in your syllabus document, so it's as straightforward as that, and you're supposed to memorize it. Now remember, the intermolecular forces of attraction between the molecules exist because these are non-metals, and we used to understand that there are weak forces of attractions between their molecules. The melting and boiling point increase down the group, and this very reason is going to affect this one. The halogens are all covalently bonded molecular substances. The melting boiling point increase as the mass increases. Since the ones on top are lighter ones, for example, fluorine and chlorine, hence they are gases at room temperature with low melting and boiling point. Then comes bromine, which is a liquid. This means definitely with the increase in molecular mass, the state of matter changed, the melting and boiling point increased a little bit. And finally, with iodine, with such a big structure, there is more attraction, there is more molecular mass, and the attraction becomes stronger, so much so it's a solid at room temperature, and it has the highest melting and boiling point among the whole group, if only first four elements are considered. So we understand as the mass increases, the intermolecular force of attraction becomes stronger. We need more energy to overcome these stronger forces of attraction. Remember, no covalent bonds are broken when we either melt these or boil these. Since they are non-metals, they are poor conductors of both heat and electricity. Acetylene is radioactive. It is formed during the radioactive decay of famous elements such as uranium and thorium. Most of its isotopes are so unstable that their life can be measured in seconds or fractions of seconds. So that's why it's still a mystery to human beings. It decomposes so quickly that we are not able to study it in time. Now, all the halogens, my bad, all the halogens are extremely poisonous. They're toxic. So we need to understand the safety precautions. Fluorine is dangerously reactive. You never find it in a school lab. Apart from any safety problems due to the reactivity of fluorine and chlorine with most of the substances around them, with air, with water, and they are extremely poisonous and present in terms of vapors, they're handled to be in a fume cupboard. So whenever we do any experiments with fluorine or chlorine, or if we are trying to produce them as a result of an experiment, we do the experiments in fume cupboard. Fluorine apart, I'm just talking about fluorine. You will never see an direct experiment with fluorine or production of fluorine in a school lab. For chlorine, we use a fume cupboard. If fume cupboard is not there, remember it has to be extremely well ventilated space, and serious precautions are supposed to be taken because this is really poisonous. Okay, so moving on. Liquid bromine is also very corrosive. Great care has to be taken to keep it off the skin. As soon as it interacts with skin, it eats the skin away. This happens for other ones as well. So we make sure that we keep all of the halogens away from direct contact. Be it ingestion, be it touching, be it inhaling. You need to stay as far away from them as possible. Reactions of halogens. Now, halogens reactions are based on many things, and we are going to consider different reactions with different products. Now, the book is simply going to keep writing the reactions and talking about them. They hardly use any headings like they used for this one reaction, but I tend to talk about them in terms of headings. That's better. So, these first portion is for hydrogen halides. Hydrogen halides, when dissolved in water, form the most uh, common acids in the planet. So, these are the reactions to form acids. These are the reactions to form salts. So these are different reactions with different products in mind. All right. To start off with hydrogen halides, halogens, all of them react with hydrogen. And the way that they form their product depends upon this very name, hydrogen halide. So fluorine is going to form hydrogen fluoride, chlorine is going to form hydrogen chloride, bromine is going to form hydrogen bromide, so on, hydrogen iodide. I hope you get the idea. And every time the equation is the same, just replace it in another halogen instead of bromine. There you go, you get your equation. So the equation for fluorine is going to be the same, which means we literally just replace Br with F, and there you go, you have got your answer. So that's about it. So you should be capable of writing any of their equations. Moving on, hydrogen halides are acidic poisonous gases. In common with all the substances formed between halogens and nonmetals, these gases are covalently bonded. They are very much soluble in water. As soon as we dissolve them in water, they form solutions of acid. For example, hydrogen chloride, when dissolved in water, is commonly known as hydrochloric acid. It produces something so different that we need to give it a separate name. Hydrogen chloride is simply a gas dissolved in water. It's one of the strongest acids of the planet. Not very strong in terms of strong, but strong as well as most used. That'd be right if I quote it like that. Now, moving on, they react with alkali metals or other metals. It's not just about group one, it's not just about alkali metals. Yeah, these are the most used salts, but they also form salts with transition elements and with alkaline metals or group two metals as well. To start with, alkali metals are the best possible example. Sodium burns in chlorine with typical yellow flame, produces a white solid, which is sodium chloride, the salt we eat every day. So I hope you get your answer that this salt is produced by a burning reaction. So much so we do not perform this reaction in lab. It's a little bit violent reaction. So we try not to mix any alkali metals and halogens in school lab. It's an ionic solid, which means every time they're going to react with a metal, they're going to form an ionic solid, no matter which halogen we are talking about. So if we're forming white sodium chloride, there would be a similar reaction with bromine, and it would form sodium bromide. I hope this naming pattern gives you the idea how we name them. So the similar stuff is given over here as well. For example, if HCl is hydrochloric acid, HF would be hydrofluoric, HBr would be hydrobromic, and HI would be hydroiodic acid. And they produce these separate ions in water. Although they are covalent compounds, they should not be dissolving in water. But not only they dissolve in water, they actually react in water and produce ions, and hence that acidic effect. So, moving on, these were the three important reactions to begin with. But another important category of reactions would be displacement reactions. Displacement reactions are what halogens can do among themselves, and the idea is very simple. The reactivity decreases down the group, which means anyone above would be more reactive than anyone below it. So much so that we can react the substances or the halogens above with their salt solutions of the halogens at the bottom, and they would simply displace them. Take a look at this reaction. This reaction is really interesting. Potassium bromide can react with chlorine. Chlorine is present on top of bromine. So chlorine would be capable of displacing bromine, forming its own compound, and pushing bromine aside. This is only possible if the single element is the halogen above in the group and the salt one is below in the group. And the exact opposite happens. The one below is separated in the form of element, and the one above forms the salt. We use the words that chlorine is more reactive than bromine, so it has displaced bromine. Remember, we're using the term it displaced bromine, not bromide. This is not correct. This is the hint that has already been written over here. All right. Pure liquid bromine is red brown. When we dissolve it in a solution, it becomes orange. When it's too dilute, it becomes yellow. So that's fine if I write this one as colorless solution. This is a very colorful experiment. This one is a pale green gas. Now this one again is a colorless solution. But since the solution can dissolve bromine, so it becomes a little bit of an orange or a yellow solution. So a colorless solution is converted into yellow, and that gives us the idea that reaction has been proceeded and there has been a displacement. Similarly, if potassium iodide is reacted with chlorine, since chlorine is more reactive than iodine, it can displace it, form a compound, potassium chloride, and push iodine apart as in the elemental form. Again, a brown or an orange, or maybe if it's very dilute, a yellow solution would form. To give you the idea, from colorless to yellow, the reaction has occurred and there has been a change. In the same way, potassium iodide solution can be used with bromine, and since bromine is more reactive than iodine, it can displace it and form the elemental iodine. Again, in this case, we may have a red or an orange or a yellow solution. You can see the solutions over here and here. What if we do the opposite? What if I take a potassium bromide solution like there is over here, and we try to react it with iodine? Now, iodine is less reactive than bromine. With the reaction occur? In order to cater the answer to this question, they have written these three rules at the bottom. They're going to give you the idea that these experiments show no reaction. So if you're asked a question about these three, you simply write the phrase no reaction. Take a look at this. Bromine cannot displace chlorine out of potassium chloride solution. Why? Because bromine is less reactive. And the same happens to iodine. It can't displace chlorine out of potassium chloride solution, or it can't displace bromine out of potassium bromide solution. Why? Iodine is less reactive than both. And this I can easily prove from this small diagram. Imagine iodine is present at the bottom, so it cannot displace anything. Here we haven't drawn fluorine. If we have considered fluorine among the list, so fluorine would be capable to displace fluorine, bromine, and iodine. It is capable of displacing any of them, but if we talk about iodine, it is not capable of displacing any of them. Why? Iodine is the least reactive one, or why in the case of fluorine? Because it's the most reactive one. Get the point? Are you there? Can you hear me better?
Yes, sir.
Okay, good. Moving on. The displacement reaction we just talked about, we need to put them in ionic equations because they are better, they are more easily understandable, and they give us the idea which ions were exactly involved in the system. The ions that don't do anything, and in that case, your book clearly tells us the metal ion don't do anything in these reactions. It is known as a spectator ion. So notice we can cut the metal ion from the whole equation, and the rest equation can be written as ionic equation. So these two over here and these two over here have been written. So the overall equation was 2 kBr plus Cl2 giving us 2 KCl plus Br2. Now, if you notice, this was an aqueous solution and this was an aqueous solution. So in aqueous solution or ionic compound can be written as positive and negative ion. Again, this is an ionic compound. It can be written as a positive or as a negative ion. What we can do is that since these two ions are same on both sides, this is aqueous, we can cut them out. You may see chlorine over here, but it's a molecule over here and an ion over here. You may see bromine over here, it's a molecule on this side and an ion on this side, so we can't really cut them out. So they're the left ones and we call it an ionic equation. Ionic equation tells you exactly the ions that are involved in this whole reaction and does not include the spectator ion. Now your book is making it very easy for you. A simple small tip. In displacement reaction, if you take out the metal, like this one in yellow, you get your ionic equation. So whichever the metal is, sodium or potassium or calcium, it really does not matter. Take it out. What you are left with is your ionic equation. And remember, we are splitting them into ions because ionic compounds dissolve in water and actually split into ions. We're not doing anything out of the ordinary. This actually happens in solution. Now, if we see the same above reaction as a redox reaction, so it should give you a very good idea what's happening. You would clearly understand that bromine is losing electrons since it's converted from a negative one state to bromine atoms, a zero state, so it's loss of an electron. Chlorine, on the other hand, is moving from zero state to negative one state, so it clearly gives you an idea that chlorine is gaining electrons. So bromine is going through oxidation. Chlorine, on the other hand, is going through reduction. It clearly gives us the idea that this whole is a redox reaction because there is simultaneous oxidation and reduction, which means simultaneous loss of electron and gain of electron, which also means that if oxidation is occurring with this one, this is a reducing agent. And as if reduction is occurring on this one, this is an oxidizing agent. The definitions to these are written over here and clearly give you that idea. So whichever the process, opposite the agent, oxidation is the process, opposite would be the agent, reducing agent, reduction is the process, opposite would be the agent, oxidizing agent. Let me give you a quick idea. The more reactive one is the oxidizing agent and the less reactive one is the reducing agent in this case. In every case, for example, we are comparing iodine and chlorine over here. So the chlorine would be an oxidizing agent and will undergo reduction reaction. Iodide ions would be reducing agents and they would undergo oxidation reaction. So that's how it works. So if you remember the tip, you're not going to have problem in non-metal displacement or halogen displacement reaction. I hope it clarifies it. So there is a similar case taken over here. In case of bromine and iodine, again, bromine is more reactive, iodine is less reactive, which should give you the idea that bromine would act as an oxidizing agent, iodide ions would act as reducing agents would undergo oxidation, and oxidizing agents would undergo reduction, as mentioned earlier. Okay, so I hope that clarifies it.
Yeah, sir.
Okay, good. So this only works for non-metals. For metals, the most reactive one is the best reducing agent. This is entirely different in non-metals. In case of non-metals, they are actually the better oxidizing agent. We can say chlorine is more reactive than bromine, but this doesn't simply just cut it. There is more explanation to it in terms of chemistry. The explanation works in such a way that we discuss their entire structures, atomic structures. Now, chlorine is more reactive because it has a strong, smaller structure. The valence shell electrons are closer to the nucleus, are more attracted, and more easily gained. So chlorine is converted into a chloride ion far more easily than it is for bromine. Why? In case of bromine, the structure is bigger, the nucleus and the valence shell electron are farther away, and it's difficult for bromine in comparison to become a bromide ion. The same argument does not apply to fluorine, so we keep it beyond the reasoning of IGCSE. You won't be asked a question about it. If you do, you need to explain that in the same way. Although that would be wrong, but you can explain it in the same way since your book says so. All right? Because at this point, we do not go with any other kind of explanation. Okay? I think this gives you a very good idea how chlorine is more reactive than bromine, or bromine in turn is more reactive than iodine, and how the pull from the nucleus helps the gain of electron faster for chlorine than it does for bromine, or how the valence shell electron is uh, farther away from the nucleus affects the whole intake or gain of electron a little bit more difficult in case of bromine than it does in case of chlorine. So if I summarize the whole set of features, group 7 elements exist as diatomic molecules. We usually denote them with X2. X refers to fluorine, chlorine, bromine, and iodine. As you go from liquid to solid, if you go move down the group, melting and boiling points are increasing. The colored poisonous vapors are there. Remember, the color gets darker down the group. You started off with pale yellow, then pale green, then red brown, then gray black. If I have to work with acetylene, which I would next in the very next paragraph, you'd understand the color gets even darker over there. When reacting with hydrogen, they form the formula HX, hydrogen halides, HF, HCl, HBr, and these hydrogen halides dissolve in water easily to form acids. They form ionic salts when they react with metals, and they can form covalent compounds when they react with nonmetals, and they react with both. They usually gain one electron and become X negative ion in ionic compounds, fluoride, chloride, bromide, the naming pattern. They become less reactive when we go from top to bottom in the group, which means fluorine is the most reactive and iodine is the least reactive when only first four are considered. And finally, anyone on the top can displace anyone at the bottom in terms of displacement reactions from their salt or salt solution. So chlorine would be capable of displacing chlorine, bromine, and iodine. Chlorine is capable of displacing bromine and iodine. Bromine is only capable of displacing iodine. However, iodine does not have the capability to displace anything, since it's the least reactive among four of these. If I talk about acetylene, it's very rare, it's radioactive. No one has ever seen a big working sample of it. But what we can predict about it would have a dark color than iodine. Dark gray or black would be a very good uh, uh, prediction about it. It would be solid at room temperature, and it would have the higher or the highest melting point among all of the halogens discussed. It would be diatomic, and the formula would 82. With hydrogen, it is going to form HAT. HAT will easily dissolve in water. It will form an acid. With metals or such as sodium, it would form NaAT, the salt, or KAT with potassium. These salts will be soluble in water. These would be white colored salts, ionic salts, in which there would be acetide ion, which forms after the gain of one electron. It would be less reactive than iodine. It won't be capable of displacing any of the halogens. However, iodine bromine can easily display, will be able to displace uh, acetylene from its salt solution. And this finishes the chapter. Now, explaining the trend in reactivity of halogens, there are two discussable points that we are about to explain, and I am going to base them as one of them is the atomic size. And if you look at it, this one is smaller in size, this one is bigger in size. And of course, the second point is very much related. The valence electron, the second point is valence electron distance from nucleus. Because nucleus is the source of attraction for all the electrons, so the distance between the valence shell electron or the nucleus is a very important factor to be considered. These are the two factors that they have considered it over here. Look, if it is small, the electron that it is about to gain and become chloride ion would be easier. Why? It has a smaller structure, so the addition of electron would be easier because the valence electron distance from the nucleus would be less, as shown in this arrow, and would easily be attracted enough for chlorine to become chloride easily. On the other hand, the structure of bromine is bigger in size. Hence, what is affected is that the distance between the valence shell electron and the nucleus is somewhat bigger or larger. So it is further away. So the attraction would not be as strong as it should be. If the attraction is not strong, the conversion of bromine from bromine to bromide ion would be not as easily possible as it was in the case of chloride ion. Okay?
Yeah.
So the attraction becomes more if the electron and the nucleus are closer to one another. The attraction becomes less if the electron and the nucleus are farther from one another. Stronger the attraction, easier the gain of electron and the whole conversion of halogen into halide ion. Farther the electron, more difficult would be the conversion of the halogen into the halide ion. And this actually explains the difference between reactivity. And based on that reactivity, we had many reactions discussed in the previous portion of the same chapter. I hope this should clarify. The
Yeah.
easier a halogen is converted into its halide ion, the faster its reactions are going to be, the more reactive it is, and the easier would be for it to displace any other halogen. And if it has a bigger structure, since the incoming electron would be farther away from the nucleus, then there would be very less force of attraction in comparison. So yeah, the gain of electron would not be as easy as and fast as it may seem for a smaller sized atom. And that's the difference. So we can easily say chlorine has a stronger tendency to form a negative one ion than bromine. So it is very easy for chlorine to be more reactive, and in turn, chlorine will take an electron away from bromide ion. So even if bromine has been converted into bromide ion by taking an electron, but that electron easily goes for chlorine. Now, I have a funny way of explaining this. All right.
Yeah.
Consider these are two rooms that are side by side in your school, and there are two different parties going on in two different rooms. Imagine both of these parties are actually birthday parties of your class fellows. Imagine the nucleus is the center table on which there are all food items that you love, right? And the outer shell electrons, this whole pink cloud, is actually the number of people standing against those that table. And imagine your chance of getting your favorite item from that table. You go into this room, right? And you see there are so many people between you and the table. You're a little bit disappointed. It would take too long for me to get to the table and find my favorite snack. You go into another room, you find very less number of people over there. You see that it's more easier to reach to the table and get your favorite snack. So you stick to that table. The same thing happens to this electron. It first goes into the room that has more people inside and it's farther from the table. It stays over there for a little time. As soon as he finds an opportunity in the upcoming atom or the other room, and it see that the table and the person and he or she would have a chance to get to the table and eat or pick his or her favorite snack, he quickly switches the room. The same thing happens to electrons. We act as our atoms do. I keep saying the same thing. Every time I explain science, I explain with our habits and I actually correlate them and I say that we act as our atoms do. So the same thing is happening in case of electrons. So it's a funny example, but it's pretty relatable. And hopefully it explains the attraction for the second room because there are lesser number of people and it's easier to get your favorite snacks off the table. Make sense?
Yes, sir. So, what about fluorine then? Like the extension one question, right?
Yeah, this is something that we can't really explain at this point because it has a couple of prerequisites. We need to discuss about more factors because I'll be honest that these two are not the only factors. There are more factors. There are two more factors. We haven't explained those two factors. The third factor is commonly known as Shielding effect. The fourth factor is known as the type of orbital in which the electron is present. So yeah, the portion in which this outermost electron is present does matter. It does really matter. So in case of fluorine, there are other factors to be considered as well. So we do not discuss it at this level. However, in advanced level, we're going to go for the whole detail and we'll discuss why this argument does not apply to fluorine. All right.
Yeah.
So, to be honest, I am not exactly answering your question because this requires more definitions. I won't have the time to explain it, but indirectly, I'm trying to tell you that there are more factors involved. Once we get to advanced level, we study those factors. After that, you'll be able to understand the argument, how this argument does not apply to fluorine, and we need a new one in terms
Okay.
of arguments or the logical points.
All
Any other
right.
questions?
Yeah.
Any other questions?
No, no, no.
Okay.
That's it.